Hi, my name is Julia Silge and I'm a data scientist and software engineer at RStudio. And we are going to tune an XGBoost model. XGBoost models are based on decision trees. They're boosted tree models, and because of this, they require very little data pre-processing, which is great. On the other hand, they have a ton of tunable hyperparameters that we have to decide what would be the best values for. And so in this video, we're going to show how to use the tidymodels set of packages to choose the best values for these hyperparameters. We're using this week's Tidy Tuesday dataset on beach volleyball matches, and we're going to predict whether a team wins or loses their match based on statistics from what happens during that game. Things like serve errors and digs and aces. Let's get started.
Okay. Let's analyze some beach volleyball. So there is quite a bit of data in this data set, which is great. This data set is let's see what we've got here. So we have there's quite a bit here. We're going to filter out a lot of these matches that don't have that have some NAs for some of the gameplay stats that we're going to use in our model. But there's quite a bit of data here, and so it's a great example data set for us to explore and walk through how to tune an XGBoost model. And so that's what we're going to do. XGBoost models can be really effective when you have structured data like this that we have. So it's a really great way for us to do this. The data isn't quite in the right shape yet for us to be able to do this model. So we're going to do a bit of some reshaping here. So right now we have one row per match. Let's look at what we have. We have one row per match. We have information about what beach volleyball circuit. This is the name of the tournament, whether it's men or women's beach volleyball. Okay, so here, and then we have information in here on the people who won and the people who lost. So this is so these beach volleyball matches are 2-on-2, two people playing two people, like pairs, and we have information on the birth dates and ages and heights. But then we have what we have in here is so the W underscores are the winners, and then over here the L underscores are the people who lost. And we have information. So here are the scores, for example, the scores of so it's best 2 out of 3 each match. And we have information on, the ranking of where they were and whatnot. But what we want to do here is we want to get out of this data set here what happened during the games. So that's things like blocks, attacks, kills, errors, aces. So these are stats that are collected during the games, and then we want to train an XGBoost model to predict wins or losses based on these kinds of stats of what happens in here. And we can try to control for things like maybe let's try to control for like the circuit, maybe whether it's men's and women's matches, maybe the year. Maybe we can see like do different does the style of play change over time, and then we want to train an XGBoost model that will be able to predict based on this information, like what goes on, what does a team do during a match, and whether they are more likely to win or lose. So you can see here we have a little bit of work to do in data reshaping, because what we want is a right now we have one row per match with information about winners and losers on both together on one row, and we need to change that. So let's take this VB matches and let's use transmute, and let's get some things out of here. So let's get that circuit and gender and year there. I think those will be interesting things to control for, maybe, and see if we see any changes or you know, differences or whatever. And then this data frame has these gameplay stats broken out by the 2 players. But let's put those together. So does a 2-person team, are they more likely to win or lose? Like, what's most important? The number of attacks, you know, if they, like, are serve errors really bad, or are errors which are different, are they really bad or whatever? So right now these are all separate from each other. So let's add these together. So for example, the attacks are gonna be, so let's find, so this these attacks plus the second person's attacks, and then we're going to do the same thing for kills. What else do we have? So we've got attacks, kills, errors. Okay, so this one will be kills. Unfortunately, there's a bunch of these, but we just have to do a little bit of reshaping here. Attacks, kills. After kills comes kills, errors. So errors. So these are the winners. How many errors did the winners make? After errors comes hit percent. If you check out the data dictionary, this is just some other things divided by each other. So I'm not going to put that in here because that is just these other things counted up, divided by each other. So that I want to put that in here because that's the same thing. But aces, as far as I know, these other things are not like subtracted from each other. They're actually counted up separately. I am not the world's, you know, biggest expert on beach volleyball, but from the little bit of research I did ahead of time. Okay, so let's call this serve errors. And so now then we'll have the serve errors and the second person's serve errors, like so. And after serve errors, we will have blocks. And for blocks, we will so the first person's blocks, the second person's blocks. How many more do we have? I think just one more. Blocks, digs. Yes, digs. And that's the second person's digs, the first person's digs plus the second person's digs. Okay, and now we gotta do all this, but turn it into losers. So we want to replace winners with losers, and let's see if I can just replace them all. I did. Okay, I think that should work. So let's see if that worked pretty well. It did. So now for some of these early years, it looks like they did not keep track. They kept track of things like aces, but not errors and whatnot. So let us let's just use an na dot omit. Yeah. so that we can, so we're only going to keep complete rows here. So let's call this VB parsed, I guess is what we'll call this. VB parsed, like so. VB parsed. So how much data we have? So we still have 14,000 matches, which is still a lot. This will still be enough for us to be able to talk about how to tune an XGBoost model. So we are going to, we've got both the winners and the losers on the same rows here, on one row per match, but we want one row per outcome. So separate rows for winners and losers here. So we're going to make two data frames and then bind them together. So first let's take VB parsed, and let's select those first things, circuit, gender, year, and let's take, first let's do the winners. The attacks through the digs, like this. And we want to get rid of this W underscore here. We want to rename them. So we're going to use, I have dplyr, the dplyr 1.0 installed right now, which is not yet hit CRAN. It should hit CRAN in just a few weeks. So I've installed from GitHub right now as of when I'm recording this, but if you watch this later, probably dplyr 1.0 will be on CRAN. So I'm going to use a rename with, where, you know, first we're of course piping in the data, and then the first thing we pipe in is the function that we want to rename with, and then what columns we want to rename. So let's do that. So we're going to say rename with, and the function we want to rename with, I'm going to just define it here with a lambda. So we're going to do string remove, let's say all, and I'm going to say the dot here because I'm piping in the ones, and then I'm going to remove those W underscores like this, and the I could say everything because the, you know, circuit, gender, and year don't have any W underscores on them, but just to demonstrate this, I'll show you W attacks to W digs like this. So this will change those names. So now instead of saying W underscore attacks, it just says attacks, kills, errors. So I think the new rename with is really nice, and I really am happy about this new feature in dplyr 1.0. And then the last thing we want to do is we want to make a new column. Let's call it win, like this. And so these are the winners. Congratulations to them. And you can probably guess what we're going to do next. Let's make losers. We are sorry for their sad times. So we'll take lose, and this needs to be an L, like that. So let's run winners and losers. Winners, losers. Okay, all right, that looks like it worked, which is excellent. And now we can make our data frame that we are going to, let's call it VB volleyball data frame, and let's bind those two together. So bind rows, winners, losers, like this. And let's change, since we're about to do some modeling, let's change anything that is a character to a factor, like this. VB df. Okay, so so these things became factors. Win became a factor. VB df. So there's two levels in factor, in gender. How many circuits are there? 2. Okay, so this is nice. Excellent. So this is ready. Let's just do a little bit of exploring here. There's there are amazing examples of exploratory data analysis on the Tidy Tuesday hashtag on Twitter that you should definitely check out. I'm just going to make one plot here to show kind of like where you might start with this. So we've got this reshape. I reshaped it this way. And let's see, of all these things like attacks, kills, serve errors, blocks, digs, and whatnot. Let's see which of these can we see visually that we see a difference between between those who win and those who lose, and which differences are biggest and whatnot. So to do that, we're going to have to reshape this once more. So let's use pivot longer. So we don't want to pivot. So which columns do we want to pivot? We want to pivot attacks through digs. So attacks through digs. And let's the names to will go to, let's call this stat for it's like a game statistic, and then values to and let's do this I don't know, let's call it value, like so. And so now we've taken this Y data frame and made it narrow, made it longer and skinny, and this makes it a good shape for making a visualization. So we'll pipe it to ggplot, and let's see, how should we do this? Let's put so on the y-axis we want value, and let's make little box plots with that are two different colors that have the win and the loss right next to each other. And what should we put on the x-axis? Let's put gender on the x-axis, and let's say value on the y-axis, fill equals win, and then let's say geom box plot like this. And let's start with that. What did I do wrong? Okay. Oh, that's all of them together. I need to facet wrap stat. And those will need to be, those are some of those are big and some of those are small, so we'll need to make that. All right, that is looking pretty good. Let's make it n row equals 2 so that they're more spaced out there. And I'm gonna say color equals win, because I prefer the look of that with a nice low alpha like that. And sometimes when I make a plot like this where I've taken things that are on different scales, and I'll just say y equals null, because it's pretty obvious what that value is. And also when I have like a win over here on the legend, I'll just say like color equals null. I guess I'll say fill equals null too. Okay, let's look at this. All right, let's make this bigger so we can take a little look here. Re-render. Okay, nice. Okay, so we've separated out the men's and the women's matches so that we can see differences here. And the matches that were lost are in the coral color, and the matches that were won are blue. And we see, as we would expect, of course, because this is how people win, is by winning points, we see these differences. So, but we see some that probably make less of a difference. So serve errors right here probably make less of a difference. Whereas, by eye at least, errors look pretty important. Blocks look pretty important. So blocks are good. Errors are bad, as we would expect. Aces look good. So we can see these differences. So attacks, interestingly, look almost like they make no difference at all, perhaps. I wonder if this 300 is an error or if that really happened, or if it's like a data error. I'm not sure. Okay, so this is like an exploratory graph that we can use to see what's in our data, understand it more deeply before we start training our model, which is always a good idea. This will be good for now, and we will get started on building our model. So let's load tidymodels. And let's start by splitting our data. Let's set a seed. And then let's split our, let me load it. And let us split our data into, so let's take that data frame and let's split it into testing and training data. So first we create a split object, and then we assign the training section of the split to VB train, and the testing part of the split to VB test. So now we have training data here. So that's nice. It's nice to have this example data set to work with that has quite a bit of data to be able to talk about something as powerful as a machine learning model as an XGBoost model. So the next thing to do is to set up our model specification. We're actually not we're gonna do no model preprocessing here, because an XGBoost model is based on trees, and decision trees can kind of handle any kind of this data. Like, it doesn't need the numbers to all be centered and scaled. These factors are fine. Like, the decision trees can handle any of this kind of data, so we're not going to do anything to it. We're just going to keep it as is. We're not going to deal with data preprocessing or recipes. So we're going to go straight to making our model specification here. So we didn't have to do a lot of data preprocessing. However, we are going to have to deal with tons of model parameters that we are going to have to tune. So let's scroll through this. Look at all these things. So much to tune. So it will take our data in whatever shape we got to it, but it takes a little bit of some doing to tune this in a sensible way. So let's talk about this. So we're gonna not tune trees. We're just gonna make sure there's enough of them. So let's take 1,000 here, and then let's talk about these hyperparameters. So these are hyperparameters which cannot be learned while we train the model. Instead, we have to train a bunch of different models at different values for these different model parameters, and then at the end say which model did best and choose them that way. So let's take like tree depth. Let's say we're going to tune it with this tune placeholder, min n, tune it, and then loss reduction, tune it. So these three, if you read about like what they do, the tree depth, min n, and loss reduction, they're kind of about like the model complexity, like how complex do we let the model get. And if you're ever interested in like how do these model parameters, what do they correspond to in XGBoost, there's a nice table down here in the documentation that says what they are. So we're going to tune all those. We're going to tune sample size, and we're going to tune mtry, which is in XGBoost it's called call sample by tree. What it is how many, when you get to each split, like how many predictors do you sample from. And so these are both kind of about like how much randomness do you put in your model, like how random do you do it. And then let's also tune the learn rate. So gosh, that's six hyperparameters to tune. It's a lot. It's a lot. We are setting, so the next thing to do is set the engine. This is, in fact, as I have been saying, an XGBoost model. So the engine here is XGBoost. You can boost trees has other arguments as well. You can also train it with either you can do it in Spark or this C 5.0 as well package. And then we need to set the mode because you can use this for classification or regression. And here we are doing classification because this is, we're trying to say, did this team win or lose their match, given the information about gameplay statistics that we have. So let's call this XGB spec. That seems good. Okay. So lots to tune there. This is going to take a while. Okay, so this is a spec, a model spec here that we have, you know, we've gotten this ready. The next thing we're going to do is we have to set up what are we going to, like, what values are we going to try? What values for this are we going to try? Okay, so there's a couple of different ways you can do this. I think one way that we often do this is with a regular grid. So this means I want to try, you know, m-try of 1, 2, and 3 and min-n of, you know, 1, 5, and I don't know, 10 or whatever. And I want to try every combination of those so that I can find the best combination. That can be a good way to go. That would take an incredibly long time with this particular kind of model. Another approach that we can take is a space filling design. So what the idea of this is, instead of making a grid and trying all the values to really narrow in on the really best one, instead we're going to make grids that cover the parameter space and fill it and fill the space like this, you know, this like 1, 2, 6, this 6-dimensional space that fill it in such a way that all the different parts of the space, we're gonna try a model in all areas of the space, kind of spread out pretty evenly. So that's the idea of these space filling parameter grids. So there's two kinds. Two, yes, the maximum entropy and this Latin hypercube, which let's do that one. Okay, so we're going to make a Latin hypercube grid, and we need to put in all our parameters here, these guys. So let's do tree depth, min and loss reduction. Loss reduction. And then sample size. Okay, so if we go back to XGBoost, the sample size here actually is, if I remember right, it is it needs to be a proportion, not a number. So what I'm actually going to do is sample size equals sample prop. Because if we do sample size is a number and sample prop is a proportion. So for this we need to say sample prop. And then we can put m-try, but notice, so sometimes these things have unknowns in them, like m-try does. And m-try has an unknown in it because m-try this, like how many predictors should we sample? Well, the smallest number we could try would be 1, but what is the biggest number? We don't know what the biggest number is until we actually have the data. So what we do, if we just put, let me show what happens if we just put mtry here. Let's keep going. Let's do learn rate, and let's say we're going to try 20 different models. You might want to go higher than that, if but let's do that for this example here. Like this. Okay, so let's see what happens here if we do mtry. Look, oh no, unknowns. mtry contains unknowns. What are we going to do? We need to finalize it. So mtry starts at 1, but we don't know where we need to start. So what we will do instead is we will finalize mtry with the data that we have. So we'll give it the training data here. So what does that give us? That it looks at the data that we have, VB train, and it uses some heuristics like, oh, all of the, perhaps all of them, to decide what would be the max that we would try here. So it uses some heuristics to decide what it should be there. Okay, so now it should work, and then we could have a grid. So we decided what the hyperparameters would be that we're going to tune, and now here we set up, here are all the different possible combinations of hyperparameters that we're going to so we're going to train a model with these parameters, we're going to train a model with these parameters, and so forth, all down these 20 possible models, and we're going to see which one performs best. So let's do that. Let's do that here. So we're going to use workflow for convenience. So we for a preprocessor here, instead of a recipe, we just can add a formula. So the formula here is when explained by everything else. So and then we can add our model. So our model here is this XGBoost model specification, and this will be, let's call this XGB workflow, like this. So this is our workflow. So let's check it out. So it has a preprocessor that is just a formula. You can preprocess. What can go in this preprocessor slot is either a recipe or a formula, something that tells the workflow what needs to happen to this data to get it ready. And then here's our model, our tunable model, which is ready. And now we need some data to tune on. So let's make let's set a seed again, and let's use cross validation. So let's take the training data. Let's make sure we have the same. Let's stratify by wins, and let's create some folds, some volleyball folds. All right, so we have 10-fold cross validation here. So this is, we have our splits into our different parts, and now this data is ready for us to actually tune. All right. So before I forget, let me set up parallel processing, because otherwise this would take so long. And let's set a seed, and let us set up our tuning process. So the first argument is our workflow. This tells us what to tune. Then we will say what is the data, the resampled data sets that we're going to tune on. And then the next thing that we'll say is what possible parameters are we going to try for our model. And then I am going to say, let's save the predictions like this, so that we can make an ROC curve at the end. And so then we can let's get this started. So let's look at what we have here. So we're tuning this workflow that we made. Oh, I can hear my fans coming on. My computer is working so hard. Okay, so and then these folds. So for each one of these folds, so each of these 10 times, we are training all 20 of these models. So that's quite a lot of XGBoost models to train. And then we're gonna evaluate and see which ones are the best. Is that right? Yes, that's right. Okay, so this is definitely going to take a moment. So I'm going to pause here and then come back once the models are done being fit. Okay, we're back. The model has trained, and that definitely took a little while. I got to go have a little break, which I guess is good and fun. But you know, this is definitely that was a lot. I mean, that was a lot of models to train. But fortunately, now we have it, and we can start exploring the results that we have. So XGBoost results. Here, so we can first, we've got a lot of things in the results here. Oh, oh goodness, I spelled it wrong, so that's silly of me. Okay, so here we've got the metrics here. So we have for all these different values of the hyperparameters that we tried, we have, let's view it here. We have accuracy and area under the curve here for all these different things. So you can see some of them, you know, are quite low, and then we have some much higher values there. So let us, you know, we can, you know, find the best values and whatnot. But let's make a visualization. So let's so this is a space filling design, remember. So we didn't try every combination of all the values we did. So let's only make a plot for area under the curve, and let's look at so let's take that value that's the value of the metric, and then let's see, we've got so M try. And the last thing we have is sample size here. And we are going to reshape this so that we can make a graph. So let's reshape these columns. Let's say values, wait, no names, to let's call it parameter for the hyperparameter, and then let's call it values to I don't know, value, I guess. All right, so now we have a long skinny data frame, and we can make a plot. So let's put value on the x-axis, the metric on the y-axis. Let's make these different colors. And then this is just going to be like a scatter plot, basically. So because we did that space filling design there, and we're going to need to facet for all those different parameters that we made, and definitely scales equals free x, because the y should be the same the area under the curve. Okay, so let's remember what's on the y-axis, area under the curve. So we could change that. That'd be better. The x-axis is each of these different values for these different parameters. So let's take a look at what we see here. So tree depth, it kind of goes, it's low and then kind of curves up here. So it looks like we need deep trees here. Min n, you know, maybe, I don't know, hard to say there. It looks like the higher learning rates got us there faster. So you know, you kind of take a look here and see, like, are any of these clearly better? Remember though that this is a space, we tried a space filling design, and so we can't pick off the best value here in the same way we would if we did, you know, trained a regular grid, but we can understand a bit about our results from exploring this in this way. When an XGBoost model like this, often, so let's say like show best for these XBG, whoopsie daisy, ROC, area of the curve. So here are the 5 best models. So notice they have pretty different parameters here. So like this one has a bigger learn rate, this one has a bigger loss reduction. Some of these values aren't super far apart, but this is but we can get, I can't quite see the area under the curve. Let's get over here and see. That's not that far apart from each other, right? So we can get to the same performance with different combinations of these parameters. That's kind of a characteristic of XGBoost models here. Let's select the best one, the one that performed the best here. And just to, I think this is probably clear, but if we wanted to try more models, we would bump up this number. If we wanted to sample more finely across the possible values for all of these different parameters, or if we wanted to zoom in, like say we only wanted to try things at the high tree depths and whatnot. Okay, so let's find the best one. So we put in the results. Let's say AUC here, and let's call this best AUC. Best AUC. So this is the one that has the high learn rate. It does not sample as many at the splits, and it has, you know, pretty deep trees and whatnot. And now what we'll do is we're going to finalize the workflow that we have. So our workflow is XGB workflow. I put the letters in the right order on that one. And let's call it best AUC, and we will call this final XGB, like this. And let's take a look at it and see what we see. So so we've got the same preprocessor. Instead of having all these things just say tune, now they have values. So the loss reduction is tiny, the learner rate's, you know, pretty big-ish, you know. So now we have all these values that we picked via tuning. So that's our fit model. That's our fit model. So let's do a few more things before we call ourselves done. For example, XGBoost is a model that we can get variable importance out without too much hassle or trouble. So let's take that this model, let's fit it to the training data. VB train. Then we will pull out the fit, and then we will send it to the variable importance function. And then also VI is variable importance, VIP is variable importance plot, like so. So this will make a plot for us of variable importance for this XGBoost model, and we'll say what were the biggest contributors to the classifications, one way or the other. So this is fitting. This is the VIP package needs a little bit of an update here. So let's zoom in, make this big so it's easier to see. Okay, so what are the things that contribute the most to the classifications? So kills is biggest, errors is big. So these are the two things that are most important in of these things here that make the biggest difference in a win versus a loss: kills and errors, and then attacks, which was interesting because that was one that we didn't see a huge difference in the plots. It looks like year, not, that's not very big, and the circuit made almost no difference. Gender, very small difference. So we don't see big difference between men and women in this. Serve errors was very small. So we're able to see what are the relative importance, say, of errors. Like errors are a big deal. Serve errors are not a big deal. We're able to understand that from this kind of plot, which is super helpful to be able to get this kind of information out from an XGBoost model, which to be able to understand what's driving the predictions. And finally, let's do the last fit. Like this. So what last fit is it says we want to fit the final best model to the training set and evaluate on the test set. So we will say, so last fit. So we give that final XGBoost. All we have to send is the split object, and let's call that final result here. And we can collect the metrics and see. So these are evaluated on the test set. So we're training on we're fitting on the training set, evaluating on the testing set here at the very end. And we could so we'll be able to say, like, were we overfitting? Okay, so our ROC here is 925, and our best ROC, did I ever print it out? We would have to look at the plot again. Plot. Okay, so our best ROC here, was 9. Yeah, okay, so that looks pretty good. So I don't think we have evidence here that we did not overfit during our tuning procedure, which is excellent. And so this is evaluated on the testing set. So we did well with our tuning procedure by not overfitting. And what else can we do with this? We can also not only can we collect the metrics. Oh, I forgot my parentheses. We can collect the predictions, get out the predictions. So these are predictions. Notice the number here. These are predictions on the testing data, not on the training data. So, this one was right, this one was wrong. Oh, a fair amount wrong there. So we can do things like, we can do things like a confusion matrix with truth, and then predicted class, like this. We can see, a confusion matrix. We also can do an ROC curve, and here we say the truth, and then the probability of of win, right? I think this is right. And then we can auto plot that and make an ROC curve where we can visualize the results of our of how our model performed at different thresholds for the true positive and false positive rates here. So this is a work. We walk through this whole workflow for the XGBoost model using this this data on these volleyball matches, and are able to look at the model first, or look at the data first, get ready to tune, and then explore the results that we have at the end.
Okay, we did it. We tuned our XGBoost model. We tried a whole bunch of different hyperparameters. We found the best one for the data that we have. We found that that kills and errors are the things that happen in games that are most predictive of whether a beach volleyball team is most likely to win or lose. We used a space-filling design to of all these different hyperparameters for the XGBoost model that we could try to make sure that we were able to try enough different kinds of values to be able to cover the space of all the different kinds of parameters that were there. So XGBoost models, I'm sure most of you know, perform really well in situations when you have structured data like this, and when people in machine learning competitions, people have really good results with them, and they have really good results in real life situations as well. And you can also understand why from a globally, like what drives their predictions, which also is really nice. So they can be a really good option in certain situations. I hope this is helpful, and I will see you next time.